All right, so this is Unit X. It's sort of a review of a lot of things that we've done and a couple of new things just to make sure you can move on with chemistry and any other science and understand what's going on. So, we have already talked in some length about how there are reactants and there are products, and there's an energy difference between those two, and then there's an activation energy that any reaction requires to sort of get to what we call in chemistry an activated complex. So this is sort of the area where this can either fall back to reactants or forward to products. And the difference in energy between the reactants and products is called the enthalpy. It's signified with a delta H in this case because you're going overall in a downward fashion from hydrogen and oxygen to water. That would be minus 572. So that would be exothermic reaction. The reactants have higher than the products. If you think about, well, what about water going back to hydrogen and oxygen? Now, the activation energy is much larger because it has to overcome not only the activation energy the original reaction, forward reaction had, but also that enthalpy difference. So there's a larger activation energy to go back, activated complex still, and then it'll fall this way. That'll change your delta H to a positive number. And another way to think of activation energy, right? If you think about a bird, whether it's going to a lower branch or a higher branch, it always kind of jumps up a little bit, right? So there's a little activation energy. That's sort of what that curve looks like. All right. So the reversible reaction, like we just saw, would have the same enthalpy, but now it's positive because you're going up the hill instead of down the hill. The activation energy would be much larger because now it has to overcome that enthalpy. So let's take a look at an interactive about this. So here you have a bunch of water, let's say, and it's trying to get back to hydrogen and oxygen, and this wall is basically keeping it there. So if I give these molecules more energy, then they're going to be able to maybe find one that gets up there and can clear the wall. Let's see if that happens. It does not seem to be happening yet. All right, so there we go. Now we got some things going over. So it takes a lot more energy, but this is why we say it's a reversible reaction, right? They don't all have to go forward. They can go stay where they are, or some of the ones that were over here can come back. When we talked about driving forces were things that would make sure the reaction would go one way or the other, not just stay on one side of things. So this is has no driving force, so it's going back and forth in this case. Okay, so let's go back to this, and then okay, so a catalyst, what a catalyst is going to do, and you may have heard this term before, and a catalyst is similar to, not even similar to, the enzymes you see in biological situations and processes. That's sort of what a catalyst is, but in chemical processes is not near as complex often. It's just, it's usually more boring, basically. What it does is, though, it's going to increase the reaction rate, and it does that by it's not going to change that enthalpy. The difference in the heights of the reactants and products is not going to be any different. What it does is it lowers the activation energy, and by lowering the activation energy, it's easier to achieve the activated complex. So let's go back to what we were just looking at here, which is here. So what a catalyst would do is lower this wall barrier, so now more things can get over, if that makes some sense. And now it's a little easier for those red things to become green and for those green things actually to go back to being red. But that's what a catalyst does, is it doesn't take near as much energy now to achieve what you had to achieve before. It doesn't change the heights of these. There's still more energy in this reactant than this product. However, it does make it easier for, basically the wall goes down, so it's easier for things to happen like that. All right, so let's continue with that. All right, and that's what we just did. So what is an activated complex? An activated complex is basically the situation where two things can react. Now, let's say hydrogen needs to react with chlorine. If hydrogen hits chlorine in the way so that the HCl can form, then that's what the activated complex would look like, right? It's not going to be helpful if hydrogen comes at chlorine from a situation like this, because now this hydrogen is not going to have anywhere to connect. This one kind of does. This chlorine has nothing to connect to, so that's not considered. We're making some stuff up here because we don't really know what's going on. But based on some studies, that's what they're thinking is the orientation of the molecules is correct so that something like that can happen. And that's called an activated complex. And catalysts, we do know this, will help orient things so that they can react better. And that's true of biological enzymes as well. They kind of put things in the right position. Receptors hold things so that everything's lined up to happen properly. So what a catalyst does then is it provides an alternate reaction pathway. So when I was just doing that, we were just doing this, right? I said it lowers the activation energy. The activation energy is going to be this high for that pathway, but what a catalyst might show is a different way for this red to become that green and say, hey, and you know what? If you do this way, it doesn't nearly require you as much energy to do it. So it's an alternative pathway to achieve the activated complex. And often it'll just put things in the proper orientation. That's sort of the alternate pathway, but otherwise it could sometimes provide an electron when necessary to get things moving a little bit better. The key, though, here is that reactions, the catalyst is often released at the end of the reaction, so it can go do it all over again. So it's recycled. So you can have A react with a catalyst, turn into B, and then the catalyst goes back and finds another A to hook up to and do it all over again. So catalyst, and then there's such a thing as poisoning a catalyst. It's possible that something besides A will stick to that catalyst. This happens a lot in chemistry. A lot of catalysts in chemistry are metals, and so you'll have a metal surface, and certain things will stick to that metal surface, like a double bond might stick there very well, and you've got that all lined up. So it's possible that the area here that's attracted to that double bond can get poisoned. It can get sort of occupied by something like a sulfur. And so now that catalyst won't work for that carbon double bond to come in because that sulfur is blocking the area that the carbon double bond would have been in. We could say that's poisoned. Okay, and again, that's something you may have heard a similar situation happening with catalysts in biological functions. All right, so the last thing we're going to talk about is energy in reactions. So here, this water reaction, if you put hydrogen and oxygen together, you make water and a whole lot of energy gets released. In fact, this is sort of the pipe dream of cars. If we can use hydrogen fuel for cars, it would make water as a byproduct. We wouldn't be unhappy about that like we are carbon dioxide. So because the energy is released, the enthalpy would be negative because that means that hydrogen and oxygen are higher than this water, right? And that's what we're just looking at with all these things, right? The hydrogen and oxygen is higher than the water. So in the direction of hydrogen and oxygen going to water, they have to go down. So the enthalpy is negative. If it was going in the reverse way, if water was going to hydrogen and oxygen, it would need that energy in. So the enthalpy would be positive. So this enthalpy is good for this reaction. So that means 2 moles of hydrogen will make 2 moles of water with 1 mole of oxygen, and that much energy will be released. So if we say how much energy is produced with 1 mole, right? If we made 1 mole of water, that would be half as much. So we'd have half as much energy. So 572 divided by 2 would be how much energy 1 mole of water produces. What if you released 4 moles of hydrogen instead of 2 moles of hydrogen? Well, if you released 4 moles of hydrogen, that's twice as much. So if it makes sense, that would be 572 times 2 in that case. All right. So, and again here, if you want to make 1 mole of hydrogen, that would be the same thing as 1 mole of water, right? It would be half of 572. So hopefully that makes sense. It sort of brings everything together with stoichiometry, energy of reactions, that kind of thing. So this is another aside. The issue with hydrogen fuel is hydrogen is a legit gas, right? And we learned how 1 mole of gas at standard temperature and pressure will occupy 22.4 liters. So if we're doing that reaction that we just saw and we had 2 moles of hydrogen, that would occupy 44.8 liters. To compare that to octane, which is gasoline, 1 mole of that, because it's a liquid, will give you significantly more energy than 1 mole of hydrogen. Okay, that's 2 moles of hydrogen is 572. And then plus the volume that a whole mole of octane occupies is significantly less than 22.4 liters. So hydrogen fuel cars would require very high pressure to store it in a low volume. And in fact, I just read something this week in the news that someone found a way to have that hydrogen take up less space. Basically, there was some sponge, is what they were calling it, but basically something that would hold the hydrogens closer together so that you didn't have to have such a high pressure of it. Anyway, hopefully you all can figure that out before our energy issues happen. So nitroglycerin, this used to be a thing in childhood cartoons. They used to play around with that. If you remember the Daffy Duck thing that I showed you when we were doing the solutions lab, he had just swallowed nitroglycerin before he blew up. So anyway, this is very explosive because look, all these nice gases like we have on Earth, right? Oxygen, carbon dioxide, nitrogen, water. The reason these things exist on Earth in such abundance is because they're very low energy. So this is a much higher energy and it's going to a much lower energy. So that's why it's explosive. So if we're going to balance this equation, and I gave you four of those nitroglycerins is how the balancing starts. And you're going to go to those. So if we have 4 of these, that's going to give us 4 times 3, 12 carbons. So you know there's going to be 12 carbon dioxides because that's where all the carbon goes. And the hydrogen all goes to water. So 4 times 5 is 20. So that's telling you that's 10. 4 times 9 is 36. Some are going here. 10 already went there. Some are going here. So 12 times 2 is 4. 12 times 2 is 24. Plus 10 is 34. And we had 36. So that means there's just 1 oxygen. And then all that nitrogen, the 12 nitrogens go there. So it should be that. Let's see if I'm right. 6, 12, 10, and 1. Yes. So do you expect the energy to be a reactant, so something on this side, or a product? Based on what I just told you, that all these things are very stable, that we find them on Earth all the time, that things like to be like that. Hopefully that makes sense to you, that energy is going to be a product. And that this is going to release a whole lot of energy, as shown in Daffy Duck. How many kilojoules are in 1 mole? So does it make sense that if that's the kilojoules for 4 moles, if we wanted 1 mole, we would divide this by 4? And what do you think the energy diagram would look like? So in your energy diagram, which is higher, the reactants or the products? So hopefully you realize the reactants are going to be higher than the products, right? These are all very stable, lower energy. So that delta H, that enthalpy, is going down from here to here. And it's 22,880 kilojoules. A little bit of activation energy to get that thing going. And, right. So the last thing I want to talk to you, though, said that was the last thing, is equilibrium. Now, we talked about thermal equilibrium, and thermal equilibrium was when temperatures were equal. This is not true of chemical equilibrium. So chemical equilibrium is not thermal equilibrium. That seems to be something that gets people confused on exams. So chemical equilibrium does not equal thermal, where everything reaches the same temperature. Chemical equilibrium is not a matter of reaching the same temperature or same ratio. Think about during school, back when we were in school, there were a certain number of people out of school, right? Because they were late or had appointments. And then most of the people were in school. And that was the equilibrium. We had about 90% of people in school and maybe 10% of people were outside of school. And maybe one would come back from that appointment and another one would have to leave for that appointment and another one would show up after waking up and another one would have to leave because of a sale at Lululemon or whatever. So we have a ratio that maintains of 90 to 10. So we would say that was like the chemical equilibrium of the school at that time. Then we can have a big reaction, a big situation that would change that. And that would be, let's say, the bell at the end of the day, right? And at the bell at the end of the day, that equilibrium is now going to change and a whole lot of people are going to leave. Now, some people stay behind, right? They have extracurriculars, they're at sports, they're at drama or whatever. And so the same thing's going to happen. Maybe someone shows back up because they forgot a book because someone's leaving, but you're going to have a change in equilibrium, and it's no longer going to be 90 to 10, but the equilibrium would now be much more like 80% are out of the school and 20% are in the school after the last bell. All right, so this is similar to what my cat does. The cat can be awake or the cat can be asleep, and if I were just walking around and I'd make a little hash mark every time I saw the cat doing one thing or the other, I can keep a track of his equilibrium. And maybe he's awake. He's not near awake that often. Maybe he's awake 5 out of every 12 times I see him. So, 5 of the 12 times I see the cat, he's awake, and 7 out of 12 times he's asleep. So that would be sort of the ratio of his equilibrium. So that's what we're talking about with chemical equilibrium. Chemical equilibrium is the amount of reactants and products. They stay consistent with time, that when one goes one way, the other goes the other way. And we can affect this by doing things. Just like with the cat, if I tried to introduce something with the cat, like a bird in the house, right, I'm going to have the cat awake much more if there's something in the house that's of great interest to him versus asleep, right? And I can also make him sleepy by having other things happen. So let's take a look here. So the equilibrium here, you can see, is sort of 12 to 31. For every one that goes over one way, one comes back. And right when I said that, it's apparently going to be more like, oh, there, 12 to 31, it's back. So we can change this equilibrium by not using a catalyst, right? If we don't use a catalyst, that equilibrium could change where it's harder for those red to become green. So maybe now we'll have more red than green. We could heat it up, right? That could get more of that red to make it go over. We could cool it down. That would make it harder for the red to get over. So these are things we could do if we produce gas as part of our reaction. So if we have a reaction that produces gas, we could increase or decrease the pressure. These are all things we could do to affect equilibrium. So that is that, I think. I think that's all we had to do. And that's it. Yeah. All right. So there's 3 assignments. Go pick one and enjoy the rest of the week.